All right, and we're live. This lesson it's called Zombie Battle System because that's been the theme of the tutorial. But what's really important here is payable functions and how to build dApps that accept money from players. I think that's a very key part here. Anyway, let's start. Chapter 1, Payable. Up until now, we've covered quite a few function modifiers. It can be difficult to try to remember everything, so let's run through a quick review. Awesome. I love reviews. It looks like my green screen color is a little bit off. Let me play around with that just for a second. You know what it is? The time of day has changed, so you'll get to see me sitting in a green screen. Let me pick a color. This seemed to be a good spot. Okay, turn it back on. There we go. That's a bit better. The time of day has changed, so the sun angle has changed, which color changes the color of your green screen. Anyway, so let's get to this review. Hold on. Close. All right, let's get to this review. We have visibility modifiers that control when and where the function can be called from. Private means it's only callable from other functions inside the contract. Internal is like private, but can also be called by contracts that inherit from this one. External can only be called outside the contract, and finally public can be called from anywhere, both internally and externally. We also have state modifiers, which tell us how the function interacts with the blockchain. View tells us that by running the function, no data will be changed. Pure tells us that not only does the function not save any data to the blockchain, it also doesn't read any data from the blockchain. Both of these don't cost any gas to call if they're called externally from outside the contract, but they do cost gas if called internally by another function. I made more coffee, and guess what? There's a water follow-up. All right, anyway. Then we have custom modifiers, which we learned about in lesson 3, only owner and above level, for example. For these, we can define custom logic to determine how they affect a function. These modifiers can all be stacked together on a function definition as follows. Function test external view. And view means it's only reading data. Someone from outside the app is calling it, right? That's what they said. External can only be called from outside the contract, right? Only the owner, and some other modifier. In this chapter, we're going to introduce one more function modifier, payable. All right, the payable modifier. Let's put some coffee. All right, payable functions are part of what makes Solidity and Ethereum so cool. Just to note, it's been pretty cool so far. They are a special type of function that can receive Ether. Let that sink in for a minute. When you call an API function on a normal web server, you can't send US dollars along with your function call, nor can you send Bitcoin. But in Ethereum, because both the money, Ether, the data, transaction payload, and the contract code itself all live on Ethereum, it's possible for you to call a function and pay money to the contract at the same time. This allows for some really interesting logic, like requiring a certain payment to the contract in order to execute a function. Contract, online store, function, buy something, external payable. Check to make sure that 0.001 Ether was sent to the function call. Require that your message value, remember we have message sender who tells you who it is, value is equal to 0.001 Ether. If so, do some logic to transfer the digital item to the caller of the function. Okay. Here, message.value is a way to see how much Ether was sent to the contract, and Ether is a built-in unit. What happens here is that someone would call the function from Web3, the dApp's JavaScript front end, as follows. Assuming online store points to your contract on Ethereum, online store.buy something from Web3 ETH default account value Web3 utils to WEI 0.001 Ether. Notice how the value field where the JavaScript function call specifies how much Ether to send. If you think of a transaction like an envelope and the parameters you send to the function are the contents of the letter you put inside, then adding a value like this is like putting cash inside the envelope. The letter and the money get delivered together to the recipient from, and then value, you put it in the envelope. Buy something and you're passing a dictionary. Message.value. Okay. So let's recall that message is global, so we don't have to pass it here. But if you give it a dict here on the front end to buy something, I guess that's the message. I guess we'll find out later. Anyway, if a function is not marked payable and you try to send Ether to it as above, the function will reject your transaction. Putting it to the test, let's create a payable function in our zombie game. Let's say our game has a feature where users can pay ETH to level up their zombies. The ETH will get stored in the contract, which you own. This is a simple example of how you can make money on your games. Awesome. Let's see. uint level up b is equal to 0.001 Ether. Create a function called level up. Function level up. And this will take one parameter, a uint called zombie ID. I think if we're passing the ID, okay. Anyway, it should be external and payable. So I think we do external payable, right? External payable function. Let's go back down. The function should first require that message.value is equal to level up fee. It should then increment the zombies level. So do zombies of zombie ID dot level plus plus, increment it. And let's put a little space here and close that space there. Let's check our answer. Beautiful. Little guy runs across. All right. Chapter 2, withdraws. In the previous chapter, we learned how to send Ether to a contract. So what happens after you send it? After you send Ether to a contract, it gets stored in the contract's Ethereum account, and it will be trapped there unless you add a function to withdraw the Ether from the contract. You can write a function to withdraw Ether from the contract as follows. Contract get paid is ownable. Remember we wrote this class ownable over here? Or it's like the template that everyone uses, right? Function withdraw external only owner. Address payable owner. You get an address of uint 160 owner.transfer this address balance. Right, so you're looking at, let's see what's going on here. You're getting the address of the owner. You get the balance. Okay. Anyway, note that we're using owner and only owner from the ownable account. Let's notice it. Where is only owner? Using owner and only owner. From the ownable contract, assuming that it was imported. It is important to note that you cannot transfer either to an address unless that address is of type address payable, but the owner variable is of type uint160, meaning that we must explicitly cast it to address payable. Once you cast the address from uint160 to address payable, you can transfer ether to that address using the transfer function, and address this dot balance will return the total balance stored on the contract. The address of this is the contract, so this is what we sent in to return the total balance stored on the contract. So if 100 users had paid 1 ether to our contract, this balance would equal 100 ether. You can use transfer to send funds to any Ethereum address. For example, you could have a function that transfers ether back to message.sender if they overpaid for an item. Ether, message sender, transfer, blah, blah, blah. Or in a contract with buyer and a seller, you have the seller's address in storage. Then when someone purchases his item, transfer him the fee paid by the buyer. In a contract with the buyer and seller, you could save the seller's address in storage. Then when someone purchases his item, transfer him the fee paid by the seller. Seller.message, message.value. These are, wait, what? In a contract with a buyer and seller, yeah, you could save the seller's address in storage. Then when someone purchases his item, transfer him the fee paid by the buyer. Message value, seller.transfer. Yeah. These are some examples of what makes Ethereum programming really cool. You can have decentralized marketplaces like this that aren't controlled by anyone. Putting it to the test. Create a withdrawal function in our contract, which would be identical to the get paid example above. The price of Ether has gone up over 10 times in the past year, so while 0.001 Ether is about $1 at the time of this writing, if it goes up again by 10x, 0.001 ETH will be $10, and our game will be a lot more expensive. So it's a good idea to create a function that allows us as the owner of the contract to set the level up fee. Create a function called setLevelUpFee that takes one argument, a fee, that's external, and uses the modifier onlyOwner. The function should set the level up fee equal to _fee. Okay, create the withdrawal function here. And I said it's just going to be identical to this. Withdraw only owner, payable, convert it, transfer it to the owner. Okay. So it's a good idea to create a function that allows us as the owner of the contract to set the level up fee. Function level up fee. That takes one argument, uint _fee. And it is external. And it is only owner. And it should set the level up. Set level up fee. So do we have level up fee lowercase somewhere? Yeah. Fee is equal to _fee. Cool. Excellent. All right. Well, this is a shorter one. Now that we've learned about payable functions and contract balances, it's time to add functionality for zombie battles. Following the format from previous chapters, we'll organize our code by creating a new file, contract, for the attack functionality that imports from the previous contract. Put it to the test. Let's review creating a new contract. Repetition leads to mastery. If you can't remember the syntax for doing these, check zombiehelper.sol for the syntax, but try to do it without peeking first to test your knowledge. Declare at the top of the file that we're using Solidity, that version, import the helper, declare a new contract called zombie attack that inherits from and leave the contract. All right, so is it pragma? No. Yeah, it's pragma Let's just double check ourselves. Solidity. Okay, yeah. Let's see, we're gonna do import double quotes dot slash zombie helper dot sol. Do these need semicolons on them? Or this? Yeah, they need semicolons. Okay, and then we're going to make a contract called zombie attack, and that is a zombie helper. And I said no. Why is zombie helper lowercase? All right. Is zombie helper and leave it blank. Okay, check our answer. What? It is, right? Yeah, it is. Look, contract is blah. Imported zombie helper. What don't they like? Do I need a semicolon up there? Yes. Of course. There we go. Just a semicolon. Okay. Chapter 4, random numbers. Great, now let's figure out the battle logic. All good games require some level of randomness. So how do we generate random numbers in Solidity? The real answer here is you can't. Well, at least you can't do it safely. Let's look at why. Random number generation versus CAC, I guess. 256. The best source of randomness in Solidity is the hash. We could do something like the following to generate a random number. Rand nonce, random, you call it with something, mod 100. Increment it. What this would do is take the timestamp of now and the message sender and an incrementing nonce number that is only ever used once, so we don't run into the same hash function with the same input parameters twice. It would then pack the inputs to convert them into a random hash. Next, it would convert that hash into a uint and then use mod 100 to only take the last 2 digits. This will give us a totally random number between 0 and 99. This method is vulnerable to attack by a dishonest node. In Ethereum, when you call a function on a contract, you broadcast it to a node or nodes on the network as a transaction. The nodes on the network then collect a bunch of transactions. Try to be the first. In Ethereum, when you call a function on a contract, you broadcast it to a node or nodes on the network as a transaction. The nodes on the network then collect a bunch of transactions. Try to be the first to solve a computationally intensive mathematical problem as a proof of work, and then publish that group of transactions along with their proof of work as a block to the rest of the network. Once a node has solved the proof of work, the other nodes stop trying to solve the proof of work, verify that the other node's list of transactions are valid, and then accept the block and move on to try and solve the next block. This makes our random number function exploitable. Let's say we had a coin flip contract. Heads, you double your money. Tails, you lose everything. Let's say you use the above random number function to determine heads or tails. Random is greater than 50, random less than 50 is tails. If I were running a node, I could publish a transaction only to my own node and not share it. I could then run the coin flip function to see if I won. And if I lost, choose not to include the transaction in the next block I'm solving. I could keep doing this indefinitely until I finally won the coin flip and solved the next block and profit. So how do we generate random numbers safely in Ethereum? Because the entire contents of the blockchain are visible to all participants, this is a hard problem, and its solution is beyond the scope of this tutorial. You can read this Stack Overflow thread for some ideas. One idea would be to use an oracle to access random number functions from outside of the Ethereum blockchain. Oh, is this a link? This is a link. Let's take a brief look over here. Let's take a moment to make sure we confirm my choices. I'm running a smart contract. Generate random numbers. There are a few trade-offs. Yeah. Yeah. It's hard. Anyway, here's a way to kind of do it. Blah, blah, blah. Okay. It's a fairly involved thing. I believe it. Okay. Of course, since tens of thousands of Ethereum nodes on the network are competing to solve the next block, my odds of solving the next block are extremely low. It would take me a lot of time or computing resources to exploit this profitability, but if the reward were high enough, like if I could bet $100 million on the coin flip function, it would be worth it for me to attack. So while this random number generation is not secure on Ethereum, in practice, unless our random number function has a lot of money on the line, the users of your game likely won't have enough resources to attack it. Because we're just building a simple game for demo purposes, in this tutorial there's no real money on the line. We're going to accept the trade-offs of using a random number generator that is simple to implement, knowing that it isn't totally secure. In a future lesson, we may cover using oracles, a secure way to pull data from outside of Ethereum to generate secure random numbers from outside the blockchain. Put it to the test. All right. Let's implement a random number function we can use to determine the outcome of our battles, even if it isn't totally secure from attack. Give our contract a uint. All right, start here. Uint rand nonce, and set it equal to 0. Create a function called randmod, and it will be an internal function that takes a uint named underscore modulus external returns a uint. And in this function, this function should first increment rand nonce, so rand nonce plus plus. Using the syntax rand nonce plus plus. Finally, it should be in one line of code. Calculate the uint typecast of the CAC 256 hash of that and return its value. That was a mouthful. If you didn't, yeah, they're saying do this with a couple changes. So let's check it out. Finally, it should calculate and return. Okay. Encode packed. Now message sender rand nonce modulus. And that should be it. Oh, nope. Does external come after returns? No. What did I do wrong here? Function rand uint modulus returns int rand nonce. Oh, thank you, checking program. That's the big no-no in Solidity, internal versus external. Huge mistake. All right. Chapter 5. Now that we have a source of some randomness in our contract, we can use it in our zombie battles to calculate the outcome. Our zombie battles will work as follows. You choose one of your zombies and choose an opponent's zombie to attack. If you're the attacking zombie, you will have a 70% chance of winning. The defending zombie will have a 30% chance of winning. All zombies attacking and defending will have a win count and a loss count that will increment depending on the outcome of the battle. If the attacking zombie wins, it levels up and spawns a new zombie. If it loses, nothing happens except its loss count incrementing. Whether it wins or loses, the attacking zombie's cooldown time will be triggered. This is a lot of logic to implement, so we'll do it in pieces over the coming chapters. Put it to the test. Give our contract a UN variable called attack victory probability and set it equal to 70. All right. Give our contract uint attack victory probability and set it equal to 70. Create a function called attack, and it will take two parameters, uint zombie ID and a uint target ID. And they should be external functions. Leave the function body empty for now. Okay. Awesome. On to chapter 6. Refactoring common logic. Whoever calls our attack function, we want to make sure that the user actually owns the zombie they're attacking with. It would be a security concern if you could attack with someone else's zombie. Can you think of how we would add a check to see if the person calling this function is the owner of the zombie ID they're passing in? Well, you would pass it to the thing and do the check owner or whatever. Give it some thought and see if you can come up with the answer on your own. Take a moment. Refer to some of our previous lessons code for ideas. Answer below. Don't continue until you've given it some thought. Well, the thought is you add that modifier. Yeah, say they're talking about it down there. We've done this check multiple times now in the previous lessons. Change name, change DNA, feed and multiply. We've used the following logic. Require if the message sender is the owner of the zombie. This is the same logic we'll need for our attack function. Since we're using the same logic multiple times, let's move it into its own modifier to clean up our code and avoid repeating ourselves. Woo! Put it to the test. We're back to zombiefeeding.sol. Since this is the first place we used that logic, let's refactor it into its own modifier. Deal. Modifier. Owner of. And I'll take one argument. uint. Zombie ID. The body should this thing. All right. You can refer to zombiehelper.sol if you don't remember the syntax for a modifier. Am I missing something? Zombie helper. Let's see. Modifier. Nope, just like a regular function. Oh, that's right. That's their hint. This like odd underscore thing. Modifier, baby. Okay. If you don't remember this syntax for a modifier, change the function definition, feed and multiply. Such that it uses the modifier owner of. Now that we're using a modifier, you can remove the line require message sender. Okay. Yes. Remove this line. Yeah. Thanks for the heads up. Is that it? Nope. Something's wrong. Modifier owner of uint zombie ID. Zombie helper. Modifier. Blah, blah. Blah, blah, blah. What's wrong here? Modifier is in the contract, right? Yep. Let's see what they're saying. A space again. modifier, space. Try again. No, something was really wrong here. The body should require that zombie to owner of zombie ID, message.sender. What's going on here? Show answer. Internal owner of. Oh, and I gotta pass the argument. There we go. Okay. We have a couple more places. Update, change name. To use owner of. So we put it here. Owner of underscore zombie ID. And blammo. Same here. We'll copy. We'll copy. We'll paste like a professional. Take this out. And we'll check our answer. Perfect. All right, back to attack. Enough refactoring. Damn it. We're going to continue defining our attack function now that we have the owner of modifier to use. Okay. Put it to the test. I love it. There's the put it to the test. Add the owner of modifier to attack. Deal. Owner of. So prepared for this. Zombie ID. Oh, not prepared at all. ID. Okay. The first thing our function should do, excuse me, is get a storage pointer to both zombies so we can more easily interact with them. Okay. Zombie storage my zombie and set it equal to zombies of zombie ID. And let's make enemy zombie. And this will be zombies of target ID. We're going to use a random number between 0 and 99 to determine the outcome of our battle. So declare a uint named rand and set it equal to the result of rand mod 100. Okay. Deal. Check answer. Yes. All right. Zombie wins and losses. For our zombie game, we're going to want to keep track of how many battles our zombies have won and lost. That way we can maintain a zombie leaderboard in our game state. We can store this data in a number of ways in our DAP, as individual mappings, as a leaderboard struct, or in the zombie struct itself. All right, hold on. For the zombie game, we want to keep track of how many battles our zombies have won and lost. This way we can create a zombie leaderboard in our game state. We can store this data in a number of ways in our DAP, as individual mappings, as a leaderboard struct, or in the zombie struct itself. Each has its own benefits and trade-offs depending on how we intend on interacting with the data in this tutorial. We're going to store the stats on our zombie struct for simplicity and call them win count and loss count. we're going to store the stats in the zombie struct for simplicity. Easy enough. Add new properties here. You got it. UN16s today. UN16 win count. And a UN16 loss count. All right. I keep scooching away from the microphone. Since we can pack uints, yeah, they give some reasoning for UN16 is big enough, but not too big, so we can pack it. Now that we have new properties on our zombie struct, we need to change our function definition in create zombie. Change the zombie creation definition so it creates each. All right, so we got to initialize. Hold on. Since we all right, now that we have a new property in our zombie struct, we need to change our definition and create zombie underscore. Okay. Create zombie DNA. Zombie creation definition. 1. So that each new zombie with, all right, so where's the end parenthesis for this? Cooldown time, and we're going to do 0, 0. Awesome. That is non-annoying syntax. Anyway, chapter 10. Now that we have a win count and loss count, we can update them depending on which zombie wins the fight. In chapter 6, we calculated a random number from 0 to 100. Now let's use that number to determine who wins the fight and update our stats accordingly. Put it to the test. Create an if statement that checks if rand is less than or equal to if rand is less than or equal to attack victory probability. If this is true, then our zombie wins. Increment my zombie's win count. Do I have a my zombie? My zombie. That win count plus. I don't know if this is right. Don't I have to index somewhere? Or is that just it? It's the zombie ID? All right. Yeah. Yeah, it's not the owner. It's the actual ID of it. Okay, my zombie. Wait, what? If this condition is true, our zombie wins. So enemy zombie. Okay. My zombie dot level plus and enemy zombie dot loss count plus. Run the feed and multiply function. Check zombie feeding dot soul to see the syntax for calling it. Zombie ID, target DNA, memory, species. So they're saying feed and multiply. Do I need to include it? Zombie feeding. Okay, so I think it has it because of all the inheritance. Feed and multiply by calling it. Let's see. My zombie, okay. It needs the ID, right? Feed and multiply zombie ID with, for the third argument, what's the second argument? It doesn't actually do anything for the moment, but later we can add extra functionality. All right, so let's put a comment there, and let's put zombie for now. But have we used feed and multiply before? Feed and multiply. Target DNA. I guess target DNA. That's not right. Well, first off, that's not right. But yeah, is it my zombie.dna? What don't they like here? What's going on? If rand space on the, and here we got what's going on here. Enemy zombie.dna. Okay. My zombie, and then that zombie. They want a space there. They want a space there. And we still got some sort of error. Yes, the missing semicolon. All right, there we go. Okay. Ooh, this one's going pretty fast. We're at 42 minutes so far for this lesson. Chapter 11, Zombie Loss. Now that we've coded what happens when your zombie wins, let's figure out what happens when it loses. In our game, when zombies lose, they don't level down. They just add a loss to their loss count. And their cooldown is triggered, so they have to wait a day before attacking again. To implement this logic, we'll need an else statement. Else statements are written just like in JavaScript and many other languages. So, start here. Else, like that. Put it to the test, add an else statement, and this is for losers. My zombie dot loss count plus plus. Increment the enemy zombie. Enemy zombie dot win count plus plus. And then we're going to run. All right, so we're going to take the my zombie dot outside the if else. Let's see. Feed on multiply, feed on kitty. Withdraw level up, change name, get zombies by owner. Create zombies, ownable. My zombie is a zombie type. Zombie type, okay. Where is trigger cooldown at? Trigger cooldown. It takes a zombie type. And it is of the zombie feeding class. Else, of course, they want the space. Okay, so it's just here in the namespace. Okay. What's going on here? I have too many spaces now. Okay, what else is going on here? Oh, it should be in? Only if you lose, I thought. Okay, whatever. There we go. We have battled. All right, wrapping it up. Congratulations. This concludes lesson 4. Go ahead and test out your battle function to the right. After winning the battle, your zombies will level up. Your zombie will increase his win count. You will spawn a new zombie to add to your army. Go ahead and try the battle, then proceed to the next chapter to complete the lesson. I attack, slain in battle. Slain in battle. What happened? When do I get a new zombie? Do I get it? Or is this just a battle? What happened? Do I not feed and multiply? All right. Congratulations, you have completed level 4. I've added a new level 1 zombie to my army. Cool. Proceed to next lesson. And with that, we have finished number 4 in the beginner to intermediate smart contracts. Next, we have crypto collectibles and app front end and Web3.js, which I'm really excited about. Thanks for tuning in. Please like and subscribe, share it with your friends, tell everyone you know. Love to get some followers. And thanks. Bye-bye.